So we're going to do these optimization problems all at once, even though just depending on the days during a normal school day, it's sometimes split over 2 days, just depending on how far we get. This is the worksheet I would want you to look at and just keep that off to the side, but I'm going to do the work on a separate sheet of paper, mostly because I don't want to be planning space. I want to just kind of have this loose and fresh and open. So let's start with the first one. The first one asks for, let me flip back over really quick. I've got different 3 screens up. Which points on the graph y equals 4 minus x squared are closest to the point 0, 2? So we're going to actually turn on a grid. You're going to want to see a grid. So maybe do these notes on graph paper just to get a good sense of what's going on. Okay. So let me just kind of come back to this. This was y equals 4 minus x squared. So y is equal to 4 minus x squared, and it wants to know which points are closest to the point 0, 2. Okay, let's get a graph looking at 4 minus x squared just to get a sense of what we're talking about here. This is sort of my fail-safe, where if you don't know what you're doing or you're really not confident in what you're doing, then simply try to graph it and just get a sense for what this may look like. Can't promise that's going to be best in every case, but at least it will give you a sense of what you're doing. So 0, 2 is going to be a point right here, and 4 minus x squared is basically a curve that starts at 0, 4, and we know it has roots here, so I can kind of just draw a graph of this inverted parabola coming down like this. The question asks which points, which definitely means that we're talking multiple points. I want to see if I can pause this. I don't even know if I can. Maybe not. Okay, I'm going to worry about it. So the points that are closest, I don't know what point that is. We're going to put a arbitrary point here, and I'm going to call that point x comma y. And what I'm looking at is a function that describes the distance between those 2 points. So if I want a function that's truly describing the distance between those, then we need a distance formula. Distance is equal to, I know this is 0, 2, and maybe instead of xy, I'm going to call this x comma 4 minus x squared. So distance is equal to the big radical of the change in x squared plus the change in y squared, and that would be a 4 minus x squared minus 2 squared. And if you need to review the kind of classic distance formula, then please do so. That's something that should be just fresh in your heads, that distance is equal to the square root of the change in x quantity squared plus the change in y quantity squared. So in this case, what we end up with is the distance is, well, you know, what my goal is going to be this. My essential goal in these is to find a prime. So since this is distance with respect to x, or d of x, my goal is to take d prime of x and set d prime of x equal to 0 and figure out what points that happens. Well, in this problem and in this problem only, I'm actually going to try a slightly different strategy. I'm going to create a second function. I'm going to call it r of x, and that's just going to be the radicand, which is the thing inside the radical. And I'm doing this because at the places where the d of x is optimized, basically the place where you have the smallest distance, it's also going to be the place where the inside of the radical is the smallest. Same x value, so I might as well use the simpler function. We're going to simplify r of x. This is x squared plus 2 minus x squared squared, or r of x is equal to x squared plus 4 minus 4x squared plus x to the 4th, or r of x is equal to x to the 4th minus 3x squared plus 4. Okay, so that's the r. Now we're going to do a derivative, r prime of x. R prime of x is equal to 4x cubed minus 6x, and I want to figure out where that's set equal to 0. So let's factor. We're going to factor a 2x out, and I get 2x squared minus 3 equals 0. or I get x is equal to 2, or x is equal to plus or minus root 3 halves if I solve that. Now, what we have found are the x values where mins or maxes or some sort of change is occurring. To truly get a sense for what's happening here, we want to do some sort of analysis of what these mean. Meaning, it's not going to be enough just to say, yay me, I found mins and maxes. What I have to really do, absolutely have to do, is to show whether these x values are mins or maxes. So I can do this in one of two different ways. What I can do is I can do a first derivative test. Since I already have this, the first derivative test would mean that I need to actually kind of truly factor this derivative out, which would be 2x, and then technically, well, we don't have to really factor it. You just need to be careful with your sign test. I know that if I plug in a super large number, I'd get a, let's plug in all my critical values, sorry. Positive root 3 halves, negative root 3 halves. Plugging in a super large positive number would be a positive. This would actually factor technically, well, I'll show it anyway. It technically factor in a root 2x minus root 3 and root 2x plus root 3 as different factors where that came from. So crossing over root 3 halves means that you'd be getting a negative, then you get a positive and then a negative there. So that's kind of essentially what's going on with this. And then what you need to be thinking is that mins or maxes occur. Mins or maxes occur anywhere where you're crossing over from negative to positive on f prime, meaning, well, here's mins, this would be a max, and this would be a min. So the question asked you back in the original to minimize the distance, which is only happening here and here. It's not happening here because this is a max point. So be wary of that. You need to somehow show that that's going on, or that you have a minimum there. Another option is to do r double prime. R double prime of x based on this thing here would be equal to 12x squared minus 6. Or if I factored it, I get 6 times 2x squared minus 1. Now, the purpose of doing that is really nothing more than to say, okay, so now what is r double prime of root 3 halves? Well, if I plug in either a positive or a negative root 3 halves, I would get something that's greater than 0, which means it comes from an area that's concave up, which means that it's a minimum at those two places. Just to test r double prime of 0, I'd get negative 6, which is definitely less than 0. So I'd come from a concave down place, and that would be a max. Okay, so we figured out the x values where that happens. I want to go back to the question and verify that I've actually answered what the question's asking. Which points are closest to the point 0, 2? Okay, which points? Points are xy values. So I need to figure out, my function was x comma 4 minus x squared. So one point is positive root 3 halves. And if I plug it in, I get 4 minus 3 halves, which translates to root 3 halves. 4 minus 3 halves is 5 halves. And the other point would be negative. So I can actually cheat and just kind of go back and say, well, plus or minus. And these are my two ordered pairs. So that's an optimization problem just in terms of distance. It's one of where you really have to keep it in your heads what the question's actually asking, like a lot of these truly do. That becomes a very, very meaningful part of this. What is the question asking, and how do I go about getting it? So let's keep moving on and kind of checking some of these. We've got 8 more of these to work through. This is going to be a lengthy video. Feel free to stop and split it up into parts if it's kind of a lot on you. Okay, next one. The next question, I'm just reading off my sheet here. I've got 3 screens up, so good to go, is find the 2 positive numbers that satisfy the requirement that the second number is the reciprocal of the first. So if the second number is the reciprocal of the first, x comma 1 over x. The second number is the reciprocal of the first. These are 2 positive numbers. I'm actually going to stop and split this video into 2 pieces. Hang on. Okay, seems to be working fine. So it says the sum is a minimum. So I'm going to create a function s of x that's equal to this sum. And so S of x is actually going to be equal to the sum of x and its reciprocal. So I've defined a function, and I'm going to write it in a different form because we know we're about to take a derivative of it. And then now I'm going to take the first derivative of this because I want to figure out at what x value is the first derivative equal to 0. So we get 1 minus x to the negative 2. Let's do a little algebra and move this around. 1 minus 1 over x squared. And then I get x squared minus 1 over x squared. So this is still s prime of x. And this is equal to 0 at, well, I mean, we don't really do equal to 0. We talk about critical values, and the critical values are 0 and plus or minus 1. So if I do a chart on this, I get 1, negative 1, and 0. And let's be aware that this derivative is actually x plus 1, x minus 1 over x squared. So the critical values of plus or minus 1, if I plug in a large number, I get a positive. It's going to be the same around 1. It'll, I think Parker's term is bounce, and around x equals 0 because you have an x squared in the denominator, so it won't change around that, and it's going to change around negative 1, giving me that. So then we have to figure out which one of these is a minimum. Well, minimums are going from increasing to decreasing. Nope. This is nope. Decreasing, increasing. So by the first derivative test, I figured out that I have a minimum at 1. So the question asks for two positive numbers. It would be x equals 1, and 1 over 1 is equal to 1. So I would just say the numbers are 1 and 1. Basically, you minimize the sum when the number is its own reciprocal. Anything else, and it's going to be greater. So let's continue. Number 3, on a given day, the flow rate of a congested road is F is equal to V over 22 plus 0.02 V squared, where V is the speed of the traffic in miles per hour. What speed will maximize the flow rate on it? Okay, the maximum flow rate is going to be, well, we want to figure out what F prime is. So this is just a practice of low d high minus high d low. So let's just kind of do it straight up as it is. Low, there we go, d high is 1, minus high, and then d low would be 0.04 V over, low would be 22 plus 0.02 V squared, quantity squared. And that is going to be equal to 0 anytime. Well, we need to simplify the numerator down. So F prime would be equal to, the 22 would hold. I'd have plus 0.02 minus 0.04, so minus 0.02 V squared over 22 plus 0.02 V squared squared. I don't need to worry about critical values from the denominator. I really just need to come down to critical values from the numerator. So where is 22 minus 0.02 V squared equal to 0? That's going to be equal anywhere that 0.02 V squared is equal to 22. Or if I multiply both sides by 50, I'd get V squared is equal to 1100, or V would be equal to, that would be end up being 10 root 11, because it's 100 times 11, 10 root 11. It could be negative root 11 as well, but our velocity itself is just asking for speed. So we know that whether it's plus or minus, we're just going to stick with the positive. Okay, let's do a second derivative test on this to prove whether it's a min or max. F double prime is equal to, F double prime is going to be tricky with this. That's not going to be fun. Let's back up and just do a first derivative test on this. So first derivative test would be, my only critical values are plus and minus the square root of 1100, which I'm just going to write it as negative square root of 1100 and positive square root of 1100. We'll put a plus or minus here on that to show this. And then way up here, if I plug in a number that's super positive, it might be helpful to realize that this is actually negative of 0.02 V squared minus 22 over 22 plus 0.02 v squared over or squared. So plugging in a super positive number is going to be positive, and then because of the factor difference of squares, it's going to bounce off. Or sorry, it's going to be negative when you plug in because we have a negative leading here. It's going to become positive, and it's going to become negative. So it wants to know where it will maximize. It's going to maximize when it's that particular value. So we can say with all confidence that the max flow occurs when V is equal to 10 root 11 cars per hour. Or sorry, not cars per hour, miles per hour. Yep. Okay. Continuing on, we go for number 4. So a manufacturer wants to design an open box having a square base, and I want to make sure your worksheet actually clarifies this because I made a subtle change. Yep, in an exterior surface area. Sorry, the source I was looking off didn't have that, but I made a note to make a change. Open box having a square base and an exterior surface area of 108 square inches. So let's do this little box here. So we got a, I've gotten better at this over the years. We do that, and then we want an open top. So we're going to draw it like that. I'm going to put this, and then dot, 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 dot that way, and dot, dot, dot that way. So that gives me kind of what I'm looking for. Any case, square base means x, and it has a height that's unknown, which means a y. My exterior surface area is going to be equal to everything that's on the outside of the box. So it's the base of the box, the x squared, plus the 4 sides. And the 4 sides are each xy's, so 4 xy's. That means that 108 is equal to x squared plus 4 xy. That means that I can actually express my y. Well, let's go with what the question's asking for. The question's asking for a volume, which is equal to x squared y. And because there's there are two x's in this expression here, we want to try to move that around to be in terms of y. So let's move it as 4xy is equal to 108 minus x squared, and y is equal to 108 minus x squared over 4x, which means that my volume function is equal to x squared times that 108 minus x squared over 4x. So the volume is entirely in terms of x. In fact, if you want to write it as v of x, that might be a little better. Okay, let's clean this up before we take a derivative. I'm going to cancel some x's out, and I'm going to factor the 1/4 out. I actually get 1/4, and I'm going to move the x's in to become 108x minus x cubed, because this is going to enable me to take a better v prime. Then I get v prime of x is equal to 108 times, or sorry, 1/4 times 108 minus 3x squared. That's that constant multiplier rule. I'm going to continue now to factor that 108. Well, let's just solve it. If I set it equal to 0, and should I show it factored? Probably. Let's show it factored. Let's take out a 3 and get a 3/4, and this is going to give me a 36 minus x squared, which clearly then we see that our critical values are plus or minus 6. So this is actually much easier now to do a v double prime of x. V double prime, if I go off of this one, it's going to be 3/4 times negative 2x. So v double prime of 6 is less than 0, and v double prime of negative 6 is greater than 0. I want the one that's going to produce a maximum volume. Less than 0 means concave down, so this one does it when you have 6. You also can't obviously have a side length of negative 6, but it's nice to see how it mathematically works out. So I can say that we have the max volume at x equals 6 inches and y equals, I'm going to have to go back up here and plug it in. So y equals 108 minus 36 over 24. which is 72 over 24, or 3. So x equals 6 inches, y equals 3 inches. It doesn't ask for what the volume is, so we're good. Moving on to number 5. Number 5, a farmer wishes to lost it again on my end. This becomes very, very, very hypersensitive because it's syncing a lot of your postings right now, so it kind of freezes on me a little bit. I'm just going to read here. Makes a small rectangular garden with one side against the barn, and he has 200 feet of fence. So you've seen these problems. I can't tell you how many times we've done these. So you have a fence, one side's against a barn. You kind of label opposite sides with one variable and label your base with another, and what you end up with should be some variant of saying that 2x plus y is equal to the 200 of the fence. So I know then that if I want to, I'm going to swing back over to this problem. If I want to max the area, then I create an area function that's equal to xy, but I want to express that in terms of just x or just y. We'll just pick just x because it's going to be easier. That's 200 minus 2x. So area is equal to, I'm going to factor the 2 out to make it an x times a 100 minus x, just to make life a little bit easier. It makes life easier on me. And then I get a prime is equal to, keep the constant multiplier of 2, and then we're going to do product rule. You don't have to, but I'm going to just to practice it. That idea of practicing things that we think we're weak in can just be a little bit better. So first derivative of the second, so first derivative of the second to -1 plus second derivative of the first. And I get a prime is equal to, this is 2 times 100 minus 2x, or 4 times 50 minus x, which means that we only have a critical value at x equals 50. So we have a critical value at x equals 50. I can actually just do a second derivative here really quickly. A double prime is equal to just -4 because it's 4 times -1. So that is less than 0 no matter what, which means that this graph is always concave down, which means that we have a max at x equals 50 feet, and y is equal to, if I go back up, y had to be 200 minus 100, so y is 150 feet, and y is 100 feet. Number 6. We have an open box with square corners. We've done this umpteen thousand times before. Open box with square corners cut from a piece of cardboard that is 10 by 10. So this is 10 by 10. And folding up the sides. So typically we don't know what the corners are, so we kind of call those little corners X pieces, and we do them off of all 4 sides, so that what I end up with when I pull those corners back up is, I need to make this to be the same height as those, so that goes like that, and this goes like that. Okay, I end up with a 10 minus 2x, 10 minus 2x, and an x folded up. Whew. Okay, so continuing on, once you fold all that up and once you get all that going, then what we need to do is volume is equal to x times 10 minus 2x squared. And I want to do the largest volume. So to do the largest volume, we need to do a little bit of v prime. Now, I've told you guys to, at various points, take the calculus or take the weakest things that you know or that you think you're weakest at and practice them. I like simplifying volume functions. I know I can factor a 2 out of this, square that, and bring it out as a 4x. Then I have a 5 minus x squared. That simple act of doing that helps greatly with just keeping your derivative as simple and as small as possible. I know it seems like a somewhat unnecessary step. I just need you to trust me that in time, those little simplifications that you can do will pay off. So practice them when you see an opportunity to use them. V prime is going to be 4 times the product rule. So first, then derivative of the second is the derivative of the inner, which is a -1. Then a 2 times a 5 minus x to the first power, plus then second derivative of the first. Remember, I kind of grouped those off. So second derivative of the first is just another 5 minus x quantity squared. Oh, you know what I kind of did before a little bit? I'm going to sort of axe this out just, well, I kind of don't want to. We'll let this go for a minute, then I want to show you something. Let's take the 5 minus x out. So I get a 4 times a 5 minus x, because there's one here, and then I'm left with a negative 2x plus 5 minus x. So if I have that, then I get a 5 minus x, and then a negative 3x plus 5. And I'm going to take a negative out of both of those so that they will cancel each other out and give me an x minus 5 and a 3x minus 5. And this is one of where, if I looked back up at this right here, I could have actually written this as 4x times x minus 5 squared, because 5 minus x squared and x minus 5 squared are the same thing. That's one of those properties of even functions that just helps greatly when you do this. So continuing on, I know that I have critical values at 5 and 5/3. And since I have critical values at 5 and 5/3, then we're just going to do a first derivative test because this is already kind of set up to be that way. 5/3 and 5, positive, negative, positive. This positive to negatives like this negative to positives like that. The question is asking me to maximize. So I know that we have a max at x equals 5/3. I want to make sure I answer what the question has actually asked me. So let's kind of come back here. We want the largest volume. Yes, 10 feet by 10 feet. So, oops. The max at 5/3 feet. And really getting this down, it wants full dimensions. I can kind of say that the dimensions of the box are, then we can go 10 minus 5, or 2 times 5/3. So 10 minus 10/3 is 20/3. The dimensions are 20/3 feet by 20/3 feet by 5/3 feet. That's when you cut off the squares of 5/3 feet on all sides. Okay, continuing on, number 7. I have to flip back over because, again, my devices are somewhat freaking out on me. Glad this one isn't, though. Box has a squared base and no top. Find the minimum exterior surface area needed if the volume is 4 cubic feet. So similar type of idea. We're going to need the surface area since the box has an open top. So surface area is going to be equal to x squared plus 4xy. And I know that the volume, which in this particular problem, it actually gives the volume. Volume is 4, so volume, which is x squared y, is equal to 4. So now this is similar to the other one, but instead I'm substituting the y is equal to 4 over x squared back into this. So that I get surface area is equal to x squared plus 4x times 4 over x squared. So I get surface area is equal to x squared plus 16 over x, or surface area prime is equal to 2x. Oops, let's rewrite this as x squared plus 16x to the negative 1. So 2x minus 16x to the negative 2. And if I factor a 2 out, let's factor the 2 out. I get x minus 8x to the negative 2, which is the same as x minus 8 over x squared, or x cubed minus 8 over x squared. Whew. Okay, that was a lot. So now I know that my critical values are 0 and 2, really. And when I do, let's just do a sign test on these, 0 and 2. If I plug in a super large number, I get a positive. Around 2, it's going to go negative, and then around 0, it's going to go negative again. So the maximum I know occurs, this is decreasing and increasing. Not the maximum, the minimum. And it wants the minimum surface area. So it wants surface area to be a minimum. The min occurs at x is equal to 2 feet. It wants what the actual minimum surface area is. So this is a new kind of problem-ish, because I want to actually plug it back into the surface area equation. So way up here, let's do this version, x squared plus 16 over x. So that would be equal to 4 plus 8, or 12 feet squared. Two more. Number 8, dimensions of the largest. Okay, bear with me. I know this is long, but you guys can pause and come back to these. I can't. I have to keep my energy up as I'm doing this. Okay, I'm going to do a little bit of a graphing on this one. It wants the largest rectangle that can be inscribed in the parabola 12 minus x squared. So we're going to call this 12. Just grow by 3s. And I'm just going to kind of guesstimate where that is. But oops. So this is going to be 0, 12, and 12 minus x squared, with 2 vertices on the x-axis and 2 vertices on the curve. So this is what it looks like when 2 vertices are on the x-axis and 2 vertices are on the curve. And here's my rectangle. So just kind of get a picture for that. You're going to see those directions a couple of times. I know that I'm going to call this point x comma 12 minus x squared. I'm going to call this point x comma 0. And I want to get in a formula for the area of this. Well, this is going to be very easy to do if you see the picture of how this is working. The area with respect to x is equal to the base, which is actually 2 x's. You should be able to very clearly see that. This is an x and this is an x. So the area of the base is 2, the length of the base is 2x, and the height here is just the function value. It's 12 minus x squared. So I get area is equal to 2x times 12 minus x squared. And that's really it. Now to take this derivative, I'm going to try to practice a different technique than product rule. I'm just going to distribute it and get a 24x minus 2x cubed. Because strictly speaking, that's easier to take a derivative of. A prime of x is equal to 24 minus 6x squared. Or if I factor a negative 6 out, I get x squared minus 4, which means that I have critical values of plus or minus 2. And if I plot those on a number line, it should be a leading negative because of that negative 6. Around the 2, it's a positive, and around the negative 2, it's a negative. This just verifies again that I've got a plus to minus becomes an increasing to decreasing. And then this would be decreasing and increasing. The question asks for a maximum, so we've got that, and I would say the max occurs when x equals 2, and it wants the dimensions of the largest rectangle. So I would just kind of, for this one, since it's a weird, I would just draw the rectangle out and say the base would be 4 and the height would be 12 minus 2 squared, or 8. So then the dimensions are 4 by 8. Units were not specified. Whew, okay, last one. And it's a little bit of a doozy, but not too bad. Find the length of the radius, the height, and the volume of the largest right circular cone that can be inscribed in a sphere of radius 8. I really wish I had a good sphere drawing tool. I don't. I have a circle that you just kind of have to envision as a sphere by like maybe doing something like that. And furthermore, when we're talking about a cone inscribed in it, that's a little bit weird. So I'm actually going to remove this and just draw a cone as a this and this and then has a kind of circular base like that. And that's a little weird. It wants the volume of the largest right circular cone. So the volume of a cone, which you should know, this is one of the ones you need to, is 1/3 pi r squared h. And all I know is that the sphere has radius 8. So what we kind of need to do is I need to put a central point in this sphere. I'm going to zoom in on this sphere and put a little central point. I'm going to call that 8. And I'm also going to connect this down to here. And I know that that is 8. And what I'm building is this right triangle right here that is made up of, well, 8. We're going to call this little r. That's the radius of the base of the cylinder. And I'm going to pull that out of the figure now so I can sketch its other side, 8r. And this is root 64 minus r squared by Pythagorean theorem. So we're going to kind of come back to the volume of this. The volume of the cone, we're going to leave it entirely in terms of r, is 1/3 pi, it should be r, pi r squared. And then the height is this whole thing, which is going to be 8 plus root 64 minus an r squared. So that's a little tricky to think about that's what's going on with this, but we can do it. So let's start taking a derivative. The derivative, first before I take a derivative, I'm going to express this volume a little bit easier as pi over 3 times an r squared times an 8 plus a root 64 minus r squared. This will give you a better sense of what you're doing with its derivative. We're just going to do a product rule. So v prime is equal to constant pi over 3. Then first, derivative of the second, you really need to be careful. We got to go derivative of the inside, which is negative 2r, then a 1/2, then a 64 minus r squared to the negative 1/2. I'm actually going to slide this underneath and move it to the left because I'm going to want a lot of horizontal space on this. Okay, then plus second derivative of the first, and the derivative of the first is 2r, so it's a 2r and then an 8 plus a root 64 minus r squared. Okay, so then pi over 3, I get, we're going to flip the order of this around, and I'm going to distribute that 2r, so I'm going to get this is going to be a 16r, then a plus 2r root 64 minus r squared. Then I'm going to have a minus r cubed. The 2's are going to cancel, and I'll have a root 64 minus r squared in the denominator. Okay, getting closer. Next little bit is we have to clean this up with a lot of algebra. We need to add this with the least common denominator. So the pi over 3. The least common denominator is going to be that root 64. So this becomes a 16r root 64 minus r squared plus 2r times 64 minus r squared minus an r cubed over root 64 minus r squared. That's your strategy to figure out how these things go when you have these big, long expressions. And I'm going to pull out everything for now except for the, and I'm going to kind of put the root 64 minus r squared so we can just work entirely inside the radical, or inside the parentheses. So this is just very much a cleanup step. 16r root 64 minus r squared. We're going to distribute here 128r minus 2r cubed and then minus r cubed. So that step is a little bit tricky, but I think you get what we're doing there. So then I get 2r cubed minus r cubed. Just checking my steps and double checking them because my work at some point here was wrong. Okay, continue on. We're going to do pi times over 3 times root 64 minus r squared. Then I have a 16r and a root 64 minus r squared plus 128r, and then minus 3r cubed. I can factor an r out. So pi 3 root 64 minus r squared. I'm going to factor an r out, so we're going to put an r, and I'm going to factor a negative out. That's going to let me flip everything around. So I have 3r squared minus 16r root 64 minus r squared minus 128. So I have one critical value now where r is 0. I have another coming from here, and nothing from here is really going to contribute to anything. So then we kind of move into just solving 3r squared minus 16r root 64 minus r squared minus 128 is equal to 0. Well, if I try to solve this with radicals like we once did, then I can have 3r squared minus 128 equals 16r root 64 minus r squared, and I square both sides. So I'm going to square the left side, which is going to give me something, square the right side, which is going to give me something. Squaring the left side gives me a 9r squared minus, this is going to be 128 times 6. Oh, I'm committing to this. 12, 16, so minus 768. This should be 9r to the 4th. 768r squared plus 128 squared. You can have a calculator, is 16,384 equals, and this would be 256. Oh, you know what? Here, sorry, way back up here, I factored an r out, so that should be away. That r should be away. This r should be away, and this would just be 256 times 64 minus r squared. Whew. Keep going. We're doing okay. We're going to have a 9r to the 4th minus 768r squared plus 16384 equals 256 times 64 is also, if you check it, 16384, then minus 256r squared. Those can cancel. You get a 9r squared to the 4th. We're going to do 768 and subtract 256, so I get 512. So I get 9r to the 4th minus 512r squared equals 0. Factor out the r squared, and I get 9r squared minus 512 equals 0, or r squared is equal to 512 over 9, or r is equal to, so 512 is 2 to the 9th, so the square root of 2 to the 9th over 3, or 2 to the 4th root 2 over 3, or 16 root 2 over 3. Whew. I'll leave it up to you to check it for positive or for mins or maximus, but that would be it. So again, a doozy, and you guys would have graphing calculators on one. I'd make those a lot easier if I was doing them by hand. So good luck.